Welcome, data engineers. Let's get started on mastering time series analysis using window functions in Apache Spark. Welcome to this deep dive into implementing window functions for time series analysis in Apache Spark. Imagine tracking website traffic. You don't just want a total count, you want the count per hour. That's what time-based window functions do. As you see in the first bullet, they group data into specific time intervals, allowing you to run aggregations like sums or averages over a timeline. Why is this critical? Because analyzing data over time uncovers trends and spikes that static aggregations miss. We accomplish this using Spark's native window function within our group by clauses. This treats time not just as a value, but as the foundational axis of our analysis, enabling advanced calculations like running counts in specific 10-minute windows. Let's look at this high-level flowchart. On the left, we have raw, continuous events flowing in. Instead of grouping by a static category like department, we project these events onto a time axis. Spark then slices this axis into discrete temporal windows like window 1 for the first 10 minutes and window 2 for the next. Each window acts as its own mini dataset, outputting an aggregated metric specifically for that discrete block of time. Now, let's break down the two foundational types of time windows Spark offers, tumbling and sliding. Tumbling windows are fixed-sized, contiguous, and strictly non-overlapping time intervals. Think of them as discrete blocks of time like computing total sales from 12:00 to 1:00, then exactly 1:00 to 2:00. Sliding windows, however, are designed to overlap. You define a window duration, say 10 minutes, but add a slide duration of 5 minutes. Because the slide is smaller than the window itself, the intervals overlap. In a sliding window scenario, a single event happening at 12:07 is actually bound to multiple windows, like the 12:00 and 12:05 windows simultaneously. Use tumbling for distinct reporting and sliding for smoothing out data via rolling averages. This diagram visually contrasts the two window types. In the top tumbling section, you see the first window runs for 10 minutes, and the second starts exactly when the first ends. There is zero overlap. Now look at the sliding section below it. The first window runs from 12:00 to 12:10, but because we set a 5-minute slide, the second window aggressively starts at 12:05. They share 5 minutes of overlapping time, meaning data points within that overlap contribute to both analytical buckets. What if your data doesn't fit into neat 10-minute blocks? What if you are tracking user behavior on a website? Users click rapidly for a while, then leave. For this, Spark supports session windows. A session window is completely dynamic. It groups events together based on continuous activity. As long as events keep arriving within a defined gap duration, say 5 minutes, the window stays open and expands. If the user goes idle and the gap is exceeded, the window closes. As you can see in the deep dive bullet, Spark even allows us to set dynamic gap durations based on the specific input row. You could give premium users a 20-minute gap and standard users a 5-minute gap using session window. This is incredibly powerful for behavioral time series analysis. Let's trace a user's session with this logical flow. The user fires an event at 12:00 and Spark instantly opens a session window. 2 minutes later, another event arrives, and Spark dynamically extends the window's boundary. A third event arrives at 12:04, extending it again. But then, notice the gap: we hit a period of inactivity. Because our defined 5-minute timeout threshold was reached, Spark officially closes the session window at 12:09, finalizing the aggregation for that specific burst of user activity. Let's look at how we actually code this. Implementing time series windows in Spark is surprisingly elegant. You use the built-in window function directly inside your group by operation. You pass 3 key arguments. First, the column containing your timestamp. Second, the window duration. And third, the slide duration. If you omit the slide duration, Spark automatically creates a tumbling window instead of a sliding one. Notice how in the how bullet we pass human-readable string intervals like 10 minutes or 5 minutes. Once you've grouped your data by this window, you simply chain your standard aggregations to the end, like count or sum. You can perfectly group by the temporal window and a categorical column, like a specific word or device ID, simultaneously. This flowchart breaks down the syntax structure of a windowed query. Your source data frame flows directly into the group by transformation. Notice how the group by splits into 2 distinct grouping criteria, our time-based window function operating on the timestamp, and a standard categorical column like word ID. These two grouping constraints merge seamlessly together into the aggregation phase, where we calculate our metric, such as a count. The result is a beautifully structured data frame, providing the exact count per word per 10-minute sliding window. Time for a crucial deep dive, dealing with late data. In the real world, IT devices lose connection and networks lag, meaning an event that occurred at 12:05 might not reach Spark until 12:20. How do we update old windows without keeping every historical window open in memory forever? The answer is watermarking. By calling with watermark and specifying a delay threshold like 10 minutes, you tell Spark to accept late data up to 10 minutes past the maximum observed event time. If an event is older than the watermark, it is safely ignored. More importantly, this threshold acts as a garbage collection signal, allowing Spark's engine to automatically drop old window aggregations from memory. This ensures your continuous time series applications never crash from an out-of-memory error. Let's visualize how the watermark acts as a gatekeeper. A late event arrives at the cluster. Spark immediately checks its internal timestamp against the advancing watermark. If the event is newer than the watermark boundary, it is allowed through and successfully updates the historic window state. However, if the event is deemed too old, meaning the watermark has already advanced past it is immediately dropped. This mechanism is exactly what allows the Spark engine at the end of the flow to aggressively clean up state memory, keeping the cluster fast and healthy. As a senior data engineer, you will often need to create multi-level rollups. Imagine you've calculated a 10-minute sliding window of data, and now you want to aggregate those results into a massive 1-hour tumbling window. You are chaining time windows. But there is a challenge. The output of the first window function is a complex struct containing a start and end time, meaning you cannot just pass it into a new window directly. Instead, we use Spark's window time function. As outlined in our How section, window time extracts a representative timestamp from the first window column. You then pass that extracted timestamp seamlessly into a second window function, enabling infinite levels of temporal aggregation. This pipeline shows chained aggregations in action. We start with raw streaming data and perform our first group by to create 10-minute aggregations. This gives us a complex 10-minute aggregated struct. Instead of stopping there, we apply the window time function to extract a clean, usable timestamp from those microbatches. We then pass that extracted timestamp cleanly into our next logical stage, applying a massive 1-hour window to create our master rollup. This tiered approach allows you to efficiently compute heavy math in smaller microbatches while delivering high-level summaries. Let's apply this to a highly valuable real-world use case: ad clickstream analysis. Imagine you are tracking a stream of ad impressions and a separate stream of user clicks. You need to know which impressions led to a monetizable click, but a click is only valid if it happens within exactly 1 hour of the impression. This requires joining two continuous time series streams. First, we apply watermarks to both streams to handle late data. Then, we perform a stream-stream join using an event time constraint. By explicitly stating in our SQL expression that click time must be between impression time and impression time plus an interval of 1 hour, Spark knows exactly how long to hold the impression state in memory. It perfectly correlates the events while strictly controlling resource utilization. Look at this clickstream architecture. We have two independent streams flowing in from the top, impressions and clicks. We immediately apply independent watermarks to each, 2 hours and 3 hours respectively, to cap our maximum memory footprint. Both streams flow into our stream-stream join engine. Here, the temporal magic happens. The event time constraint acts as a strict filter. It only passes records where the click occurred within that golden 1-hour window of the impression, ultimately yielding a highly accurate stream of monetized clicks without overflowing cluster memory. To wrap up, mastering time series analysis in Apache Spark requires understanding how to group data temporally. You have three main tools: tumbling windows for fixed blocks, sliding windows for rolling metrics, and session windows for activity-based grouping. Always remember the golden rule of continuous processing. You must define watermarks to allow Spark to clean up state memory, or your cluster will eventually crash. Finally, tune your slide durations carefully to avoid explosive computational overhead, and utilize window time when chaining multi-tier rollups. Time series functions truly transform Spark into an analytics powerhouse. Thank you for joining me. Please invite your peers to like, subscribe, and visit quicktechie.com for premium certification prep, including Q&A banks, full ebooks, audiobooks, full-length training, and interview guides. This final diagram is your optimization checklist for time series workloads. First, strictly define your required window type based on the business logic. Second, apply those essential watermarks to handle late data gracefully and efficiently. Third, continuously monitor your state memory in the Spark UI. Combining these three disciplines results in a highly optimized, bulletproof Spark application. Now go out there and start building.